Hey, hey, hey!
Come on.
Yeah, I'm back. It's just me today.
I don't need to analyze. Every word that comes out is a lie. Make it look like it's so ice. You won't make it to the finish line. If you gotta know the truth, it's gonna let you
Well, I think I'm going to have to cut that music. I can't fade it out for some reason, but here we go. All right, enough of the wacky music to start with. Thanks, everyone, for tuning in live to another Toolbox Tech Talk, coming to you from Mount Tuliwong here in the Yarra Valley. So, yeah, it's just me today. I don't have a guest. I will be bringing another guest in probably next week, and might be sort of alternating guests and then just me doing a toolbox. So, yeah, shout out to Charles, who's sitting on top of a roof in Waiheke on the beautiful Emerald Isle of Waiheke Island, just off the coast of Auckland. And g'day, James. Thanks. I'm glad you enjoy it. Oh, boy. Once again, I overdid the smoke machine. Jeez. It's really hanging around here in the studio. Look at that. Wow. It's like a disco. So, yeah, today is going to be about system configurations. And I've got a bunch of drawings which I'm going to run you through and see how that goes. Now, just check, everyone, can you hear me well? Is the audio good? All that stuff. Let's get the tech out the way. Give me a thumbs up, something in the chat. Say, yeah, I can hear you loud and clear. And there is about a 15-second delay from when I speak to when you hear me because of, internet routing dramas. That's just how things go. Anyway, let's see what I've got here for you today. I've done a bunch of little drawings, and so James says perfect. So that's what I like to hear. And I'll just adjust my little screen here. There we go. Yeah, so what's news? I usually start with what's news. Well, here in Australia, apologies to all the Kiwis out there who don't have incredibly generous government rebates because you guys just know how to do it and do it all by yourselves. But over here, our government throws some pretty big incentives to us. And the one at the moment we're all waiting for starting the 1st of July is the Cheaper Home Batteries Program, CHBP. Everyone's going to be calling it some sort of acronym, but yeah, the Cheaper Home Batteries Program, which is funded at around about $370 a kilowatt hour of battery storage, up to 50 kilowatt hours of battery storage on systems of up to 100 kilowatt hours of storage. So the first 50 is fully, it's not fully, but it's heavily funded. Which is kind of cool. But people are shouting, going, what about the other state rebates? So West Australia and New South Wales for the CPR, the PDRS scheme in New South Wales, are they stackable? Well, the West Australian government came out this week and said yes. So that's a big cheer for West Australians. You're going to get 2 bites of the cherry, one from the West Australian government and one from the federal government. We were expecting an announcement from the New South Wales government on Friday, and apparently it's good news if they don't say something on a Friday, because apparently that's what they call putting out the trash. So they usually put out the bad news on a Friday. Everyone goes home for the weekend, forgets about the bad news, and then Monday's a new world. So we're still waiting to hear what the New South Wales government's going to do about stacking of the PDRS as well as the Cheaper Home Batteries Program. So there you go. That's what's happening. For those who are just new to this, the Cheaper Home Batteries Program, the other criteria are that the systems will have to be listed on the Clean Energy Council's approved product list. So you do have to have an approved product, and it has to be installed by a Solar Accreditation Australia accredited for grid on battery or off-grid, because the program's available for off-grid and on-grid, but it has to be installed by an accredited installer. So those are kind of some of the boxes you're going to have to tick. So 1st of July is when you can actually sign off on systems, and there's already discussions on how many you can sign off on in a day. So be careful when the regulations are published. Make sure you read the fine print. Don't go, you've sold 10 systems before the 1st of July, which you are allowed to do, and install them, but not switch them on. But don't go and sign them all off on the same day, because you probably will be hit by too many systems being approved at once. So it's about doing a proper verification. So, you can't possibly do proper verification if you're just tick and flick 10 systems in a day. Yeah, so there you go. Now, let's get into the nuts and bolts of today. I think I've mentioned a few times now that we'll be installing a large battery system here at the Smart Energy Lab. I was extremely fortunate, and I have to keep a little bit confidential about who provided it, but a very generous donor donated 2.1 megawatt hours of batteries, Pylontech Power Cubes, 360 of these 40 kilogram beasts, plus 18 racks to store them in, plus 3 enormous Cynic Cell 250 kVA inverters, and a whole bunch of ancillary equipment to make it all work. But we've decided to split that system up into multiple systems to kind of spread it around the co-op here. So I live on a housing co-op. We're completely off-grid. There's 30 homes here, and we make all our own power, store it, and for, when there's a bit of a shortage, there is a bit of generator usage as well. But hopefully that will be less and less with more and more storage. We're splitting the system up. So at the moment I've been putting in nearly 800 kilowatt hours of batteries into what we call the boat shed, which is one of the labs here at the Smart Energy Lab. There's quite a lot of buildings existing. One was an old boat shed. So that's been quite a feat. 8 racks of 17 battery modules, wiring them all up, connecting them. And I'll talk a bit about that. And I'll talk about how we've integrated that extra storage into our existing microgrid. I'm also going to talk about what is a microgrid and a little bit about the different ways that you can couple energy into a storage system, what's known as AC coupling or DC coupling. So let me get my little overhead thing here. So where's my overhead? There it is. And I should have a view that looks like this. Okay, yep, there we go. There's my little overhead. Try and get it kind of clear. That looks pretty sharp to me. I hope you can all see that. So what I've got here is an explanation of AC coupling and DC coupling. What are they, and what's the terminology mean, and what variants are there? So the word coupling really is all about how does the energy from, say, a solar PV system get into a battery storage system. So solar PV is essentially DC coming out of solar panels, and batteries store DC or they store energy via DC current supplied to them. So we've got DC here, we've got DC here, but between them we have an AC network. So this blue area here is the AC network that joins the two together, and that's the coupling. So there you go. So in this case, we might have a battery inverter, which just connects to a battery and creates a stable 50 hertz in Australia and New Zealand grid, and that supplies the loads. And a solar inverter can synchronize with that 50 hertz and see it as a source. So it becomes a voltage. This is a voltage source, the battery. So it's providing, 230 volts nominally if it's single phase. And the solar inverter is a current source, and it can parallel with this battery inverter. Now, the paralleling is really quite amazing. When you think about having two sine waves generated by two different pieces of equipment, how on earth do you get them to work in unison, and how do you get the energy to flow the right way, right? So you actually want to make sure that the generation is coming from the solar first to the loads, and any surplus to the bidirectional battery inverter. So that's another point I should point out, is that not all inverters are bidirectional. Some very basic camping type inverters are designed really just to create AC power. If you try and push AC power back into them, the smoke comes out. So I have done that. So don't copy me. So yeah, you've got to make sure it's actually a bidirectional inverter, meaning it can charge and discharge from AC power. So how do these two waveforms synchronize? Well, for a start, the battery inverter is what we call the grid forming inverter. It creates a stable 50 hertz sine wave. So coming out of here, we've got a sine wave like this. There's our 50 hertz sine wave. And the solar inverter actually doesn't connect to it instantly. It sits and monitors the AC network, and it watches the frequency. So it's watching the frequency, and it can change its internal frequency before it parallels. So it's going to generate a 50 hertz perfectly in sync signal. So it'll create its own perfectly in sync signal like this. And at a zero crossing point where there is the least energy possible movement, it then will close its grid protection relay and parallel at that point. So at that point, these two sine waves are in parallel and working together. And by changing very slightly the phase angle, you can cause that current to flow. So the current will flow from the solar inverter to the loads first, and then any surplus to the battery inverter, the bidirectional, and charge the batteries. So this is a very popular configuration. What's so good about it is it's, for a start, it's scalable. So you can actually have multiple solar inverters, and they can parallel using their own internal software, and they don't actually have to be the same brand. So for instance, this could be, brand A, this could be brand B, but I've drawn this without showing a grid. In a grid connected system, you may have another input, which would be the grid. And so our battery inverter may actually have a grid input. So I'll put grid here. And the benefit of having a grid, apart from, a backup source additional to your batteries and solar, is that when these batteries are full and the loads have been met, the energy demand of the loads have been met, what happens to any surplus solar? It's still generating. It's a sunny day and your batteries are full and your loads are light. It can flow the energy out to the grid. So it can export power up to the limit that your DNSP will permit. So that's all very good. But if you don't have a grid, so if we cross that out and say it's a generating set, and typically that'll be a diesel or petrol generating set. I've said this many times, it sounds a bit funny, but you can't export electricity to a generating set and make diesel, right? It's a one-way device. So we now have a problem. If we're exporting energy through the loads, or supplying the loads, the battery's full, it can't go back to the generating set, so we have to curtail generation. So we have to somehow control this inverter so it doesn't produce more than what's required by the combination of loads and the battery. And that can be done in two ways. There's what they call generic control, and generic control is actually using one of the features built into our grid protection standard 4777 Part 2. ASNZS 4777 Part 2 is the standard that inverters that can parallel with the grid must meet, and one of the mandatory features of that is that they have a power frequency response mode by default. And what that means is if a frequency of the grid rises, the power of the inverter must reduce. Now that gives the ability for the battery inverter, which after all is the grid forming inverter, to control the generation by very slightly changing the frequency. The default values are from 50.2 hertz up to 52.0 hertz is the range where you go from 100% power down to 0% power. So that's a way of controlling the amount of generation with a small amount of frequency change. It's pretty clever. I think it was pioneered by SMA actually over 20 years ago, but it's been adopted. It's because the standards refer to it. Many inverters do this anyway, but it's still not perfect because you're going to have to consider the ratio of these two. For instance, if this is let's say this is a 5 kilowatt inverter, but we've got 10 kilowatts of AC power over here. If I'm trying to pump 10 kilowatts into a 5 kilowatt inverter, I better control it real fast because I could damage it. In reverse, it's still got the same limitations as when it's generating forward. So how do we stop that happening? Now, frequency shift, which is what this is called, frequency shift power control, can only work as fast as a 50 hertz signal, which is around 20 milliseconds from peak to peak. Now, sun can pop out from behind a cloud and you get an energy burst that's fast. Basically, solar energy works at the speed of light, funnily enough. So it may not be fast enough to control that overload. So there's often a ratio. Some manufacturers will say a maximum of 1 to 1. 5 kilowatt inverter, 5 kilowatt solar inverter. That's when you haven't got a grid to spill the surplus to. If you have the grid, you can spill that extra to the grid, but if you've got a generating set, you can't spill anything. You've just got to curtail generation. But there is another way to control the solar inverter, and that's using comms. Now, typically that'll be a wired comms. Most of the systems I've seen use RS485 over a data cable. And so that data cable that goes between the battery inverter and the solar inverter is actually controlling in data speed the output power of this solar inverter. So RS485 runs at many kilohertz, 10, 15, 100 kilohertz. So it can operate very fast. But it does now mean that this solar inverter must be compatible with the battery inverter's comms. And now we've got a much narrower range of options in terms of product. So to use some brand names here, this could be a Cellectronic SP Pro, and this could be a Fronius solar inverter, but it would need to be a what they call Cellectronic certified, because they basically program the comms to suit the way that Cellectronic want to control the solar inverter. So this would be a Cellectronic certified Fronius inverter. They have done it with other brands like ABB, Select Sun, Keiko, but those relationships have fallen away, so it's now just ABB, I believe, and Fronius. So there's an example of comms is very fast and often means that you can have a bigger ratio of solar inverter to battery inverter. 2-to-1, not uncommon. And here at the Smart Energy Lab, we were doing 4-to-1 for a trial, and it pretty well worked. We did get a few little overshoots. What tends to happen if you don't get it right is the battery inverter can go into grid protection mode, basically. What it does is it raises the frequency very quick to 55 hertz, which kicks off every solar inverter. Comms ones, generically coupled ones, that it kicks them off and they instantly stop generating. And then about 90 seconds to 2 minutes later, they start ramping up again, typically over about 6 minutes. That's the default ramp rate to full power again. So you have this kind of on-off thing happening, which isn't really elegant. It's much better to have power control that's smooth and continuous, because charging a battery, irrespective of whether it's a lead acid, a lithium or whatever, they generally like to be charged in a profile and not just in pulses of high power. So that's something to consider. Okay, so that's AC coupling. DC coupling. Now, DC coupling was actually the only way you could charge a battery up until about 20 years ago. You would have a solar array. You would have what's generically referred to as a charge controller. I'm using an example here of a maximum power point tracking charge controller, which gives you some other advantages in terms of getting the most power out of your PV array and also being able to match voltages. So if the PV array is operating at 120 volts and the battery is operating at 12, it can match them. So either side of the MPPT can be different voltages. So that's charging the battery, and then to utilize that battery either from DC loads, you could connect directly to the battery, or using a battery inverter, create AC power. So it's much more linear. Now, one of the advantages of DC coupling is DC conversion is very efficient. MPPTs are like 99% efficient. It also means that you've got two discrete systems. If your inverter were to fail, you can still charge your battery, because the battery is being looked after by the left-hand side of the diagram, whereas the inverter is creating AC power. And if you did have some DC loads, say you're doing a very small system like an RV, you probably want to run as much as you can directly off the battery and use the inverter only for those things that aren't practical to run off 12 or 24 volts or even 48 volts. But or even a small cabin, you might have DC lighting, a DC pump, but you've got AC power for appliances. So that's one of the advantages of DC coupling. So there you go, AC coupling, DC coupling. Now let me make it a little more complicated. Why don't we do DC coupling but all in one device? So what you're looking at here is what's commonly referred to as a hybrid inverter. So it can have solar connection, battery connection, and loads. And most often, it will also have a grid connection as well. So there's our grid. So it's got we could call this backup loads. Now, internally, it's DC coupled. That means the DC power from the solar panels is going directly to the batteries via an internal voltage current matching conversion. So it doesn't get converted to AC until you want to use some energy. That's when the AC gets created. And one of the other advantages of this combo here, and it does depend on the product to some extent, is I call it they can sing and dance, which means that they can charge a battery from solar, but they can also invert and create AC power at the same time, often at the same rating of the inverter. What does that mean? Well, this might be a 5 kilowatt inverter, but it actually can charge the battery at 5 kilowatts plus provide the loads with up to 5 kilowatts, because they're different power modules. One's a DC power module and one's an AC power module. So you actually can have 10 kilowatts of energy being utilized or generated by this system. So what does that mean? It means you want to have a lot more PV. If you've got this capability in a hybrid inverter, you probably want, in fact, I'd say you probably want 10 to 15 kilowatts of PV. Of course, you've got to consider the manufacturer's limits on this. So manufacturers will give you often a DC power limit or sometimes called oversizing limit, typically 150%, sometimes 200%, sometimes 250%. It's all about the product and how it's designed. Why would you want 15 kilowatts though, when the maximum you can ever utilize is 5 kilowatts of DC charging and 5 kilowatts of AC power? This might come as a shock to you, but not every day is a perfect sunny day all day long. So your 15 kilowatts of solar on a day like today, which here in Mount Tillibawong is grey and overcast, is probably only putting out 2 kilowatts. So having all that extra PV power isn't a problem. It's actually an advantage for getting more renewable energy more of the time into your system, into your loads and into your battery. And the limitations on this are that the power conversion at the inverter will often have some current limits. What they'll say is their maximum input current, IMP, and also their maximum short circuit current. Now those limits have to be considered. The IMP, which is current at maximum power, actually is the point at which clipping occurs. It's not a point at which you must not go beyond. So if you drawing a little production curve here, if you look at solar, and it often looks like a bell curve like this, if the IMP is here, what's going to happen is that bit never gets produced. We just end up with a flat topped production curve, and that's the clipping that occurs. But the other number is ISC, so that's current short circuit, and you must not exceed. Okay, so you must not exceed. And the reason for that is it's actually the current rating of the components. It could be the plug, socket, input circuitry, etc. So if the inverter were to have a short circuit internally or externally and there's short circuit current flowing, you must limit it. Now, how do you limit the ISC? By selection of modules. So the modules will have an ISC value, and so you have to match or ensure that the ISC of the inverter, so solar inputs, and the ISC of the panels are less than the inverter. In fact, there's one more requirement, which is in 5033, we put in a 25% safety margin on top of that. So that means your ISC of your module times 1.25, that's the 25% safety margin, must be less than the ISC of the input, solar input of the hybrid inverter or solar inverter. So there you go. So that's a hybrid system. Now, I'm just looking at the chat here. No questions so far. So does that mean you're all perfectly happy? It all makes sense. You don't want to throw a few curly ones at me? No? Okay. Well, I'm just keep checking the chat for any questions from time to time. All right. So let's look at the next diagram. Now, you might think you have to make a choice. Do I have an AC coupled system or do I have a DC coupled system? Well, actually, you can have both. Yep, you can have both. Now, here's an example of having both, which is I've got a hybrid inverter and it has solar connected and battery, so it has DC coupling internally. And I've got a solar inverter on my switchboard connected to the same loads as the hybrid inverter. That coupling is AC. Now, a word of caution here, not all hybrid inverters are bidirectional. Yeah, if this is the backup port and if this is the grid port, they're not necessarily all bidirectional on their backup port. So you have to check that. Quite a few inverters actually have a special port, sometimes referred to as a smart port. So it might be completely separate, and it's an AC port that can be used for multiple things. So typically for backup or for a controlled load. So you can actually connect a load to it that can be controlled. So it could be like the load only turns on when there is a certain amount of solar energy, or it could be a AC coupling port like I've drawn here. It could allow for AC coupling. So smart port, becoming more common in inverters. So that's pretty cool. All right, so AC and DC coupling, you can have both. And in fact, there's another way of doing it, and I haven't drawn it yet, so I better hang on. Let me just get a bit of blank paper before I show you the last drawing that I did, which is going to blow your mind. Okay, here we go. So this is what I call a black start protection system. Now, this really applies to off-grid. And if you've got an AC coupled system, so here's our grid forming inverter. Okay, that's our grid forming inverter. And we're connecting it to a solar inverter. So that's our solar inverter. So that's solar. And it's got some solar panels connected to it. That's the symbol for solar panels. And the grid forming inverter has a big battery system. There we go. And so this is our AC bus here. And coming off here are our loads. All right, so that's our loads. So that's basically an AC coupled system, what you're looking at there. But let's say we'll add a generator here, because if we're off-grid, you really want reliability of supply, so that we're putting in a gen set there. Now, you might think, well, that's great, because if there's no solar and if the batteries are empty and it's nighttime, I've still got a generator to keep everything alive. True. However, for those who have actually owned generators, there's probably about 10 reasons they don't work. Most commonly, low fuel, mechanical failure, the starter battery is dead because it hasn't been used for so long, the starter battery's died, etc. So this is an unreliable emergency source of power. So what a black start system using PV is to DC couple, and I'll do it in a different color, DC couple a dedicated solar charger. So DC to DC solar charging directly to the battery system. So let's say that's an MPPT, and this might be actually quite a small array. It might be just 1 kilowatt of panels, and whereas our main system is 20 kilowatts. You might think, well, what's the purpose of having just a little 1 kilowatt system connected to the battery? The beauty of this is, in a system like this with a battery inverter, so there's our battery inverter, it's the grid forming system. Now, if for any reason it shuts down, like so if our battery inverter shuts down because of it's nighttime and there's low battery status and the generator didn't start, when the sun comes up in the morning, the solar inverter won't work. Your solar inverter is going to be waiting. Sorry, I didn't put that quite in the center there. The solar inverter is waiting for a grid to synchronize with, and the grid forming inverter is shut down. So you've got a situation where you've got sun, but you've got no charge. But this little one here, putting in just a small amount of power, is going to raise the battery voltage just enough for that to wake up the battery inverter. And so the battery inverter wakes up, creates an AC supply at this point here. The solar inverter sees that there is a grid to parallel with, and it powers up, and you're back in action again. So this is your black start protection system. Now, particularly, when you're off grid and help is a long way away, this is a very nice solution. Can I also suggest that if you're going to have black start protection, that you should also have some way of charging the battery on your generating set. So put in even just a little one panel to keep the generator set battery charged up, because if you've designed this system to have a high solar fraction, that means that you hardly ever use the generator. So here at the Smart Energy Lab, we don't run the generator for 6, 7, 8, 9 months of the year. So it's sitting there, and the battery would definitely die if I didn't have a trickle charge on it. And there's a simple trickle charge to keep the generator battery alive. So there you go. That's my high reliability system with both AC coupling for the prime mover of solar energy, DC coupling for black start protection, and a little trickle charge for my genset battery to look after that, so it's being conditioned. There we go. Checking the chat. Gosh, it's really quiet out there. I can see there's quite a lot of people watching, but not much chat going on. Tell me where you're watching from, by the way. I know that Charles is at Waiheke, and I don't know where James is coming from. I'd just like to know a bit about my audience. That's always nice. So, Now, lastly, I'm going to show you a kind of really simple SLD of the Smart Energy Lab, how we have built the system here. And it's kind of an introduction to microgrids as well. So if I kind of position my thing here we go. When I don't see any chat, sometimes I worry that no one's watching. You've all just tuned off, but you haven't turned your screens off, so or disconnected. So what you're looking at here is my really basic SLD of the Smart Energy Lab. And let's start at the beginning. So we have a grid forming system. So it's a Selectronic SP Pro. It's got 6 SPMC 482s, which are 7.5 kilowatt single phase inverters, 6 of them, but they're configured in 3-phase. That means 2 per phase. And that's referred to as a power chain in Selectronic speak. So that's our grid forming system. It creates the grid, and this is the grid here. We also have, as I've been talking about it, a small black start protection system, which is just a little, 2.5 kilowatts is still quite a lot, but little MPPT-driven DC coupled to keep these batteries alive. And these batteries are, I think I've got 40 Life 4838Ps from Power Plus Energy. So that gives me around 152 kilowatt hours of usable energy in that battery bank. So that's the grid forming system. We just call it the microgrid system here at the lab. I've also got a rather old 22 kVA genset, which in the day was plenty big enough because we used to have quite a small grid forming system. And generally I would try and match these two together. It makes good sense that you are utilising the full conversion power of your bidirectional inverter. So this is 45 kilowatts of conversion power, but a 22 kVA genset is only going to put out about 18 kilowatts. And so that means this inverter has all this headroom that it could use more generator sourced power if I had a bigger generator. So probably a 50 or a 60 kVA generator would have been a better choice. You might think, well, isn't it going to use more fuel, Glenn? Actually, the efficiency goes up a little bit with larger genersets, and it might use more fuel quickly, but it generates a lot more power quickly. So you actually have a win-win. The litres per kilowatt hour is what you're worried about. The other benefit too is quiet time. Instead of this having to run for many hours, it might only run for an hour and do the same amount of energy recharge of your main grid-forming battery system. Right, I'm still checking the chat. Oh, you're totally quiet. Charles, are you still on that roof or have you fallen off? Tell me how's it going up there? Yeah, I was going to type to you. Okay, let's see if you're really there, Charles. So yeah, that's this section here is our microgrid forming system. Now, recently we've added a 50 kilowatt hybrid inverter to the mix. Now, that's a big step up, I can tell you, from having 152 kilowatt hours to, at the moment, around about 200 kilowatt hours connected to this hybrid inverter, but soon it'll be up to 800 kilowatt hours connected. We've got to connect another 6 stacks of batteries. So how did I integrate this? Well, this is where AC coupling is an amazing thing. So what's happening is there is a CT that connects and communicates, or it's a CT and a meter, so it's doing full real power, active power calculations, and that CT is telling the Solis inverter how much load there is on the microgrid. And so the Solis inverter, because it's AC coupled, it's working in parallel with the grid forming system. This inverter will try to support the loads as closely as possible. So if there is, say, all of the loads here on this network 8 kilowatts, it will output 8 kilowatts, which means that the grid forming system is basically doing nothing. It's sitting there just creating a stable grid and not even discharging its batteries. The other benefit too is you might notice I've got a bunch of other systems here that are generating sources. So I've got like 10 solar inverters, different brands, 10 hybrids, some storage inverters, etc. These will be generating as well. So we'll get some power flowing back towards the power chain. So we've programmed the Solis inverter to take its own solar and export the first 10 kilowatts back to the grid forming system to keep this battery topped up. And then anything over 10 kilowatts coming off its own 68 kilowatt array will then support the loads and charge the batteries. And that's kind of doing quite a complex set of things. And that's one of the beauties of a sophisticated hybrid inverter like the Solis 50 kilowatt. It's got some excellent programming options built into it. Incidentally, you can actually parallel a lot of these together. I think you can parallel 10 of them, so you can get half a megawatt. That's pretty cool. G'day, Charles. Good on you. You've come down for a cuppa, and you've got a slightly related question. You mentioned recently some frequency detecting switches for hot water control. What are these units? Well, perfect segue to this here. There's lots of ways of controlling generation on a closed system. Now, this is what we call an island microgrid. An island, it's not connected to the grid, so it's an island of generation and storage. And so we still have the same problem that what happens when there's too much generation, we have to curtail it. So if all the batteries are full and there's still lots of sun, which happens pretty much every afternoon and every sunny day on an afternoon, what do we do with that surplus power? We have to curtail it. But that's a kind of a waste, isn't it? Well, why wouldn't you actually try and find a use for that power? Now, one of the easiest things to use it for is for thermal loads, is to heating. Because if you've got resistive elements, and so I'm showing a hot water service here, but actually we've got, I think, 4 or 5 hot water services connected to the microgrid, and they're connected by some of them with a frequency-controlled switch, such as the Catch solar relay, or some of them via a power diverter. Now, a power diverter is something that proportionally diverts surplus power to a resistive element. And that gives you a very nice match. So if you've got 6 kilowatts of surplus solar that would otherwise be curtailed, exactly 6 kilowatts will be going into this element and heating water. These are 3-phase 9 kilowatt elements, so they've got plenty of headroom to be able to soak up a lot of energy. The other thing this does is firming. It sort of helps everything kind of stabilize. If you have got a lot, as you can see, I think I've got probably over 20 generation sources on my microgrid, including 7 homes with their own solar and battery systems that can export back to the microgrid. It's trying to get the balance so it's not sort of swinging all over the place in terms of voltage and frequency, is to have dampening. And dampening is having loads that you can bring on when there is surplus solar. And so those frequency controlled loads are really, really good. So there you go, Charles. That's what I'm using, hot water. You could also use them for things. I've seen them used for controlling oil heaters. So it's actually an oil heater that ramps up and down. Slab heating using resistive elements in the slab, or even hydronic heating via a storage tank. So that's what I've got on my house. I've got a 500 litre storage tank with a diverter connected to it that diverts power into that. And right now, it's probably heating my slab on this cold winter's day. So there you go. That helps dampen it. Now, the other thing you'll see here is we've got some EVSEs, in common parlance, EV chargers. EVSE is electric vehicle supply equipment. So it's basically AC outputs that you plug into your car and your EV to charge it. So we've got about 8 of those, so about 8 EVSEs, and that's another controlled load as well. So we can control them by things like time. So we can have schedules set so that the EVs can only charge during certain times of the day, so that helps soak up surplus solar. But also some EVSEs can integrate with comms with your solar inverter and be a direct soak. So they can proportionally change the rate they charge your car at to soak up quite a bit of power. And I haven't drawn it on here, but we've got a couple of DC fast chargers as well, a 50 kilowatt and a 25 kilowatt, fast charger. So those, they're not controlled by time, they're just available. So I tend to control them by running out of the lab and telling people to unplug because the sun's gone down. Analog control. And down the end here, we've got, like I said, 7 homes. So this is where the word microgrid actually really makes sense, is they see the microgrid as a grid. So they utilise it as the source at last resort. So when their solar and batteries aren't providing enough, they can draw on the microgrid. But conversely, they can export their surplus back to the microgrid. So they're a contributor as well. And that means that you can kind of smooth out the differences between the requirements of multiple homes. Some will have surplus and some will be in deficit. And it's a very nice thing that you're actually circulating energy between homes. Now, this is really only practical certainly in Victoria if it's a single site. Like, you're not allowed to distribute power in Victoria across property boundaries. So we're on a cooperative. There's 30 homes here. They're spread out over about 650 acres or 245 hectares. So there's 7 in close proximity to my lab, so I've connected them to a microgrid, a 3-phase microgrid. We also have some community buildings. We've got a 25-bed lodge, and it's got its own solar battery system as well. And it's also got its own frequency-controlled hydronic heating system as well. So it's another controlled load. So there you go. It's getting quite complicated. All right. Well, that's what I wanted to talk about today. And I guess it's a bit of free time now if anyone's got any questions. So it's a very quiet bunch today. I didn't blast you all with emails like I normally do. I've decided I've done enough spamming to let you know what's coming up. And because I'm pretty regular with my Toolbox Tech Talks, you can just assume that Sunday, 1 o'clock, I'll be here with something, whether it's a guest or something to talk about and explain. So I won't bombard you with spam emails going forward. One other thing I might spam you with, though, verbally, is that I'm actually going to run a microgrid course again. I ran one last year, and it was extremely popular. I had people from all around the world do it, and I ran it over 2 days, 2 3-hour sessions on a Wednesday and a Thursday. Now, of course, the timing wouldn't suit people in every country, but I recorded them and then shared the recordings with all those people who had registered. Now, that course will be a paid course. I think from memory it was $330 Australian, so whatever your currency is. But I'll announce when that course is going to happen, and I go into a lot more detail about designing a microgrid, not just from a technical point of view, but also from a compliance point of view. So there you go. Now, I see Charles has asked a question. Any regulations stopping you transferring rotary energy across a boundary, motor on one side, generator on the other side? Yeah, I know what you mean. Yeah. Well, there is in Victoria. You're not even supposed to throw an extension cord over to your neighbour's house. Though I have heard of some cheeky students in Dunedin doing something like that, where there was 1 hour of free power from one of the retailers. I think it was Octopus. And so they all chose sequential hours, and they would throw their extension cords over the neighbouring houses to get 3 hours of free power via extension cords. And if you've ever lived in Dunedin in wintertime, you know what it'll be used for, trying to keep alive. It's so damn cold and damp. Unfortunately, for our international viewers, both Australia and New Zealand suffer from the same misgivings, which is we don't realise we live in a climate that is quite cold at some times and quite wet. And so we've historically built houses that are rather poor in terms of their thermal performance. I mean, we have star ratings here. Out of 10, it's, 5 stars, 6 stars. It's really not really trying very hard. Whereas you go to Europe and it's 7, 8 stars. Some people even get right up to 9 and 10, which means that the home needs no input energy to maintain thermal comfort. So there you go. If we mandated better efficiency, things like insulation, draft proofing, passive solar design, all those things actually make for a much more comfortable dwelling and a very cheap one to run because you're not relying on energy inputs to keep it comfortable. Yeah, so there you go. I think that's my lot for today. Oh, no, I've got something else to show you. That's right. I nearly forgot. So here we go. See if I can find the screen. It's computer. There we go. So what you're looking at here is my frequency-controlled 9 kilowatt three-phase water heater on my house. Now, unfortunately, today is not a very sunny day, so we haven't got any surplus. But there's 3 bars here for the 3 elements. It's 3-phase, but they split them up over 3 elements. And so the 3 elements would ramp up and down here as the amount of surplus solar would come and go. So if I have a look at the history here, really the temperature's been going down and down and down, and there's been what are we talking, 36 watts of power coming in occasionally. But if I go back to, let's find a nice sunny day. It's been a while since we had it. There we go. There's a nice sunny day. So it's pumping in 8 kilowatts, and then the sun goes behind a cloud and then pumps in some more. And pump. And you can see the temperature's been hovering around the target, which is 75 degrees Celsius. So all the day, it's been keeping that tank hot, just using surplus solar. Now, the microgrid is monitored by switched-in storm cloud. In fact, we were a bit of a development site for switched-in the early days. And if I go back one, I think we had 22 monitoring units on the microgrid. That was an awful lot. But now I mostly just use this one, which is the main microgrid system. And so I really like this as a consumer-friendly display. It looks similar on a phone app as well. People who are not engineers can take one look at this and go, the storage, i.e. the battery, is at 40%. It's discharging because it's negative at 0.2 kilowatts at the moment. And there's nothing coming in from the grid, which in our case is the generator, and there is no solar input because we're not AC coupled any solar onto that microgrid system directly. Whereas the Solis inverter, so I'll bring up the monitoring platform for the Solis here. Here we go. So this is updated every minute or two. And there's the system, by the way, a little picture over the side here. There's a grumpy looking me. I think I was just looking a bit too serious. That little tiny box down there is a 50 kilowatt hybrid inverter, the Solis. I really like it. It's really nice. It's got all the right controls that I want. It's got a display that you can program it from the front screen. You can program it from this interface directly from the cloud. So it's great for remote monitoring. And it's got 2 independent battery ports. So you can have 2 separate batteries. They have to be high voltage batteries. So these are 700 volt battery stacks here. There's 8 of them. And we can connect them in 2 groups of 4. Now, what that means is you can expand. You might put your first battery system brand A on a battery port A, and then a little while later you decide to add more storage, and it could be a different brand and a different voltage, so that those 2 battery ports can be independent. That's pretty cool. And I did notice that it tries to balance them too. So even though they might be different capacities, it tries to bring them up to a similar state of charge so they both effectively charge and discharge equally, even though they might have different capacities. So there you go. And if I scroll back a day or 2 till I get a day with a bit of sun, where are we? There we go. There's a sunny day. So we did, it's not as sunny, it was only 65 kilowatt hours. We had some really nice days a while ago. Where are we? 119. I'm sure 174. That's pretty good. I think that was, I'm sure I saw 192. But anyway, how much renewable input that we got. So hang on. Stop clicking, Glenn. There we go. So that's that there down the bottom there is a good day. So the red line is the state of charge. So you can see the state of charge is 15%, which is the minimum I've set it to. You can go down to 10, but I'd like to give the batteries a little bit of headroom just to be sure. And once the sun come out, there's a tracking 68 kilowatt tracking array connected to the Solis inverter, and it just goes full power as soon as the sun hits it in the morning. So hence you got this almost linear rise in state of charge. And if you look at the yellow, which is the PV, it's the reason it's spiky, by the way, is we were still tweaking the frequency settings a bit. So occasionally it would pump too much power back to the microgrid, the grid forming system, and cause the frequency to spike, and it would then stop generating for a few minutes, and then it would come back online. But once we've sorted that, this should be a very flat generation profile on a sunny day. And then the sun goes down, and we're discharging the batteries in the evening. So there you go. So that's the Solis 50 kilowatt hybrid here at the Smart Energy Lab. Now I'm going to make a proper video about it. One of my channel videos explaining how it works and telling you all about it. So watch out for that. So there you go. Now I better check to see if there's any more questions that popped up while I was talking away there. No more questions. All right. Well, I think we'll call this a wrap for today. Thank you for turning up. And like I said, next week, what's the date? Actually, I'm not sure if I've got a guest next weekend, but the following I definitely have a guest, but I'll keep that to myself. And just turn up because you won't be spammed anymore with emails. So there you go. Anyway, that's all for today. All right. See you guys.